Time spent with a telescope teaches us not only how the universe is structured, but also how great our desire is to uncover its mysteries. Carl Sagan. Cosmic rays, exoplanets, interstellar objects, and the possibility of life on other planets are subjects that have always captivated scientists and enthusiasts worldwide. In recent decades, significant technological advancements have enabled us to delve deeper into and better understand the universe and our own corner of space. The diversity of phenomena and objects, such as the mysterious spokes in Saturn S rings, the heart-shaped region on Pluto, anomalous reflections on Venus, and geologically active moons of giant planets, continue to astonish and inspire researchers. Each new discovery brings more questions and possibilities, from understanding the formation and evolution of planetary systems to searching for potential traces of extraterrestrial life. Particularly exciting is the study of extremophiles organisms capable of surviving in conditions previously thought to be absolutely inhospitable to life. These organisms may hold the key to understanding what forms of life could exist in the extreme conditions of other planets and moons. One of the most intriguing hypotheses is panspermia, the idea that life or its precursors can spread throughout the universe via meteoroids, comets, and other cosmic bodies. This hypothesis, along with the study of technosignatures that might indicate the presence of advanced civilizations, expands our horizons in the search for extraterrestrial intelligence. Introducing these topics not only enriches our knowledge of the universe, but also allows us to dream of the day when we might find confirmation of life beyond Earth. As we continue to explore space with advanced technologies and international collaboration, we move closer to unraveling one of humanity's oldest and most significant mysteries. Are we alone in the universe? Beneath the frosty exterior of Jupiter's moon, Europa, lies a tantalizing possibility of vast hidden ocean of liquid water. Europa, slightly smaller than Earth's moon, has intrigued scientists since the late 20th century, when data from missions like Voyager and Galileo hinted at this secret. The moon's ice shell is believed to be approximately 10 to 15 miles thick, but beneath this frozen crust, the water ocean could be over 60 miles deep, far surpassing the volume of Earth's oceans. The potential for liquid water is made even more compelling by the presence of chaotic terrains on Europa's surface regions, where ice appears to have been disrupted and refrozen, suggesting convection from below. Moreover, tidal forces exerted by Jupiter's immense gravity generate internal friction within Europa's core, producing heat that keeps the ocean from freezing solid. This intriguing combination of factors points to the possibility of a habitable environment where the essential ingredients for life, such as water, chemical nutrients, and energy sources, might converge in ways we are just beginning to understand. This has led to speculation and intensely focused scientific inquiry, as missions like the upcoming Europa Clipper aim to uncover more about this enigmatic moon. Enceladus, one of Saturn's most captivating moons, has left scientists abuzz with the possibility of extraterrestrial life within its icy confines. With a diameter of just 300 miles, Enceladus is relatively small, but conceals a tantalizing secret beneath its frozen crust, an expansive subsurface ocean. This hidden ocean was first suggested by data from the Cassini spacecraft, which detected plumes of water vapor and icy particles erupting from fractures near the moon's south pole, known as tiger stripes. These geysers provide crucial clues about the ocean beneath, hinting at an environment that could potentially sustain life. The expelled material from Enceladus' geysers has been found to contain organic compounds, salts, and silica grains, suggesting chemical interactions between the ocean water and the moon's rocky core. These interactions could produce the energy necessary to support microbial life, similar to hydrothermal vents found on Earth's ocean floor. Moreover, the presence of hydrogen in the plumes indicates ongoing hydrothermal activity, a key ingredient for life as we know it. While scientists can't yet confirm the existence of life on Enceladus, the combination of water, organic molecules, and geothermal energy presents a compelling case. Future missions equipped with sophisticated instruments may one day pierce through Enceladus' icy shell to provide definitive answers. The hexagonal storm swirling around Saturn's North Pole is one of the most enigmatic weather phenomena in our solar system. First discovered by the Voyager spacecraft in the early 1980s, this geometric feature stretches roughly 14,000 miles across, large enough to encompass nearly 4 Earths. Unlike the more familiar round storms observed on Earth and other planets, Saturn's hexagon is a persistent and stable structure, baffling scientists with its precise angles and straight sides. The prevailing theory suggests that the hexagon is the result of a standing wave pattern in Saturn's atmosphere, similar to certain wave patterns observed in Earth's atmosphere and oceans. These waves are thought to be generated by the differential rotation of Saturn's atmosphere, where various jet streams flow at different speeds. The direct influence of a particularly strong eastward jet stream, a phenomenon known as a Rossby wave, could be propagating around the pole, creating a series of interacting winds and vortices that ultimately stabilize into the hexagonal shape. Additionally, observations from the Cassini spacecraft revealed that the hexagon extends deep into the atmosphere, up to nearly 200 miles below the cloud tops, suggesting that this unique storm is deeply rooted in Saturn's complex gaseous dynamics. The hexagon also changes color with the seasons, turning from a bluish hue to a golden tone, further indicating the rich interplay of atmospheric chemistry and solar radiation at Saturn's frigid poles. Venus, often dubbed Earth's sister planet due to its similar size and mass, defies expectations with its peculiar rotation. Unlike most planets in our solar system, which rotate counterclockwise when viewed from above their north poles, Venus spins in the opposite direction. This retrograde rotation means that on Venus, the Sun rises in the west and sets in the east. Additionally, Venus has an incredibly slow rotation, taking about 243 Earth days to complete one spin, making its day longer than its year. The exact reason for this backward rotation remains a subject of scientific debate, but several theories offer intriguing explanations. One prevalent hypothesis suggests that Venus experienced a colossal collision with another protoplanet or a series of smaller impacts during the chaotic early history of the solar system. These cataclysmic events could have altered its rotation axis and direction. Another theory points to the effects of solar tides, where the immense gravitational pull of the Sun might gradually have slowed Venus's initial rotation and ultimately reversed it. The thick, dense atmosphere of Venus, which is 90 times more massive than Earth's, plays a role as well. Atmospheric tides caused by the extreme heat of its runaway greenhouse effect could interact with the planet's rotation, contributing to the retrograde motion. Simulations and models continue to refine our understanding, but the true cause of Venus's backward spin may combine elements of these theories. Each hypothesis adds a piece to the puzzle, gradually unraveling the complex dynamics that make Venus one of the most fascinating and mysterious bodies in our solar neighborhood. Mars' tiny moons, Phobos and Deimos, present a captivating mystery regarding their origins. These irregularly shaped satellites, resembling asteroids more than traditional moons, were discovered in 1877 by American astronomer Asaph Hall. Both moons are considerably small compared to Earth's moon, with Phobos spanning roughly 14 miles in diameter and Deimos about 8 miles. Their odd shapes and surface characteristics have led scientists to ponder how they came to orbit the red planet. One leading theory posits that Phobos and Deimos are captured asteroids from the asteroid belt between Mars and Jupiter. This hypothesis is supported by their composition, which is similar to that of carbonaceous chondrites, a type of asteroid rich in carbon. However, capturing an asteroid into a stable orbit is inherently difficult, making this scenario less straightforward and leading some scientists to explore alternative explanations. Another theory suggests that the moons may have formed from debris resulting from a massive impact on Mars. Such a collision could have launched material into orbit around Mars, which then coalesced to form Phobos and Deimos. This idea is bolstered by computer simulations that show how collision debris can accrete into moons. Additionally, the inner moon Phobos is gradually spiraling toward Mars and expected to disintegrate or crash into the planet within the next 50 million years, which aligns with the theory that these moons are not stable over the very long term. Although definitive evidence is still pending, Missions like the proposed Martian Moons Exploration (MMX) by JAXA aim to uncover more insights by studying and possibly returning samples from these enigmatic moons. Such investigations could finally resolve the enduring question of their origins, adding another fascinating chapter to our understanding of Mars and its celestial neighbors. The unusual bright spots in Okator crater on Ceres have puzzled astronomers since they were first imaged by NASA's Dawn spacecraft in 2015. These bright deposits, most prominently located in the center of the crater, stand in stark contrast to the otherwise dark and heavily cratered surface of the dwarf planet, which lies in the asteroid belt between Mars and Jupiter. Detailed analysis has revealed that these spots are primarily composed of sodium carbonate, a type of salt, suggesting intriguing geologic activity on Ceres. The bright spots are believed to be the result of subsurface briny water reservoirs that have breached the surface. When this salty water ascends through fractures in Ceres' crust, it rapidly evaporates in the vacuum of space, leaving behind reflective salt deposits. This process indicates that, despite its frigid temperatures, Ceres possesses subsurface liquid kept from freezing entirely by residual internal heat, or possibly by the presence of antifreeze-like substances. Furthermore, geophysical models and data from Dawn imply that the Okator crater is relatively young, geologically speaking, having formed less than 30 million years ago. The impact that created the crater likely exposed subsurface water ice and caused subsequent hydrothermal activity, pushing the briny water upwards. This discovery on Ceres has profound implications for our understanding of the solar system's small bodies, as it suggests that even these seemingly inert objects might have the chemical processes necessary to harbor life, or at least prebiotic chemistry in their past or present. The bright spots of Okator crater are not just visually stunning, they are a beacon for ongoing exploration and study into the secrets held by the numerous worlds beyond Earth. Uranus presents one of the most striking peculiarities in our solar system, its extreme axial tilt of approximately 98 degrees. This unusual orientation means that Uranus essentially rolls along its orbit around the Sun, with its poles alternately facing the Sun directly every 84 Earth years. Understanding how this seventh planet from the Sun ended up in such an extraordinary position has intrigued scientists for decades. The prevailing hypothesis among astronomers is that Uranus' tilt resulted from a colossal collision during the chaotic early days of the solar system, when planetary formation was tumultuous and violent. It is believed that Uranus experienced a collision with a protoplanet or a series of massive impacts. These cataclysmic events could have knocked the planet onto its side, significantly altering its axial tilt. Computer simulations support this theory, demonstrating that such a dramatic tilt could be achieved by a collision with an object at least twice the size of Earth. Another aspect reinforcing this hypothesis is the existence of Uranus' moons and the peculiar orientation of its magnetic field, both of which align with the tilted rotational axis. This alignment suggests that not only Uranus, but its entire system of moons and rings were likely affected by the same colossal event. Moreover, the planet's internal structure and unusual heat distribution further indicate a history of violent impacts. These pieces of evidence collectively weave a narrative of a world that once experienced a massive transformative collision, leaving Uranus as the unique tilted giant we observe today. Mercury, the closest planet to the Sun, experiences some of the most extreme temperature variations in our solar system. Unlike Earth, where temperatures are moderated by an atmosphere and oceans, Mercury lacks a substantial atmosphere, which is crucial for stabilizing surface temperatures. This deficiency plays a significant role in the dramatic thermal swings observed on the planet's surface. During the Mercurian day, which lasts approximately 59 Earth days due to the planet's slow rotation, surface temperatures can soar to a scorching 800 F. This intense heat is primarily due to Mercury's proximity to the Sun, receiving more than 7 times the solar energy per unit area compared to Earth. The absence of a thick atmosphere means there is no medium to distribute this heat evenly across the planet or to retain it once the Sun sets. As Mercury rotates and its long night begins, the surface rapidly loses heat, plunging temperatures to a frigid 330 F. This drastic cooling occurs because there is no atmospheric insulation to trap the heat. The stark difference between day and night temperatures results from the planet's lack of an atmospheric blanket that could moderate the heat flow between day and night regions. Interestingly, Mercury's extreme temperature variations also affect its geological features. The planet's surface is continually contracting and expanding due to these temperature changes, leading to the formation of cliffs and ridges. This dynamic contributes to Mercury's rugged and heavily cratered appearance. These temperature extremes and their effects offer a glimpse into the complex and harsh environment of the innermost planet in our solar system. The Great Red Spot, a colossal storm that has raged on Jupiter for at least 400 years, is gradually shrinking. This iconic feature, once large enough to swallow 3 Earths side by side, has diminished in size considerably over the past few decades. Scientists have been observing this phenomenon with keen interest, employing both Earth-based telescopes and spacecraft like NASA's Juno mission to understand the underlying causes of this enigmatic contraction. One significant factor contributing to the shrinking of the Great Red Spot is changes in Jupiter's atmospheric dynamics. The storm is essentially an anticyclone, a high-pressure system where winds circulate counterclockwise in the planet's southern hemisphere. Historically, the red spot's vorticity, or the rotation rate of this enormous vortex, has been decreasing. This decrease in rotational energy likely results in a weakening of the storm, consequently causing its size to diminish as it loses the battle against surrounding jet streams and atmospheric turbulence that can strip away its energy. Additionally, interactions with other Jovian atmospheric features also play a vital role. The Great Red Spot often encounters smaller neighboring storms and vortices, which can disrupt its structure and siphon off some of its energy. This complex interplay within Jupiter's dynamic atmosphere leads to the gradual erosion of the storm's boundaries. Observational data have shown that these interactions can physically fragment portions of the Great Red Spot, thereby contributing to its ongoing shrinkage. Although the Great Red Spot remains an extraordinary feature on Jupiter, its continued contraction suggests that even the most powerful storms in the universe are subject to the ever-changing forces of their environments. The phenomena driving the shrinkage are a testament to the dynamic and evolving nature of planetary atmospheres and highlight the intricate interplays that govern the behavior of such immense weather systems. Neptune, the distant and icy giant of our solar system, harbors a fascinating and exotic feature deep within its interior, the so-called hot ice layer. This intriguing term refers to water ice that exists under extreme pressure and temperature conditions, vastly different from the everyday ice we encounter on Earth. Neptune's internal structure is thought to consist of a rocky core surrounded by a thick layer of water, ammonia, and methane ices, enveloped by an outer layer of hydrogen and helium atmosphere. The hot ice layer on Neptune is composed predominantly of water H2O, but in a state unlike any ice found on the terrestrial surface. At pressures millions of times greater than Earth's atmospheric pressure and temperatures reaching thousands of degrees, water molecules in Neptune's interior are compacted into exotic crystalline structures known as supermassive ice. In this state, the oxygen atoms form a lattice structure, while the hydrogen ions move freely within this lattice, creating a form of ice that is both solid and fluid-like. These conditions lead to unique physical properties, such as high electrical conductivity and increased density compared to normal ice. Laboratory experiments on Earth, using tools like diamond anvil cells and high-energy lasers, have managed to recreate these extreme conditions, providing insights into the properties of supermassive ice. These studies suggest that within Neptune's hot ice layer, the ice remains solid due to the immense pressures, even though the temperatures are high enough to melt conventional ice. Additionally, the presence of ammonia and methane can further influence the formation and stability of these exotic ices, potentially creating complex compounds not found naturally on Earth. Understanding Neptune's hot ice layer gives scientists a deeper glimpse into the physics of planetary interiors and the composition of ice giants. It also expands our knowledge of how diverse and intricate planetary processes can be, particularly in the harshest environments of our solar system. This research has implications for the study of exoplanets as well, suggesting that similar ices could exist on other distant icy worlds far beyond our own. WASP-12b is an exoplanet that stands out not just for its extreme conditions, but also for its remarkably dark appearance. Discovered in 2008, WASP-12b orbits its host star so closely that it completes a revolution in merely 1 days. This close proximity means the planet is subjected to intense stellar radiation, heating its atmosphere to scorching temperatures exceeding 4,000 F. Such extreme conditions have intriguing implications for the planet's physical characteristics, especially its albedo or reflectivity. The primary reason WASP-12b is one of the darkest known exoplanets lies in its atmosphere's unique composition and its interaction with the intense radiation from its star. Unlike more reflective planets, WASP-12b absorbs almost all of the light that hits it, reflecting back less than 6, making it even darker than fresh asphalt. This extraordinary absorptive capability is largely due to the presence of atoms and molecules like titanium oxide, vanadium oxide, and iron hydrides in its atmosphere. These compounds are highly efficient at absorbing visible light, trapping the stellar energy and converting it to heat rather than reflecting it away. Compounding this dark appearance, the extreme heat on WASP-12b also prevents the formation of reflective clouds or hazes that are commonly found in the atmospheres of other gas giants. Without these reflective layers, the planet lacks the bright, shiny clouds that would otherwise bounce light back into space. Observations from the Hubble Space Telescope and other instruments have been crucial in identifying these absorptive materials and understanding the complex atmospheric dynamics at play. The study of WASP-12b continues to offer valuable insights into the wide variety of atmospheric conditions that can exist on exoplanets and the mechanisms that give rise to such dark, light-absorbing worlds. WASP-12b's exceptional darkness provides a stark contrast to the more familiar reflective gas giants in our solar system, showcasing the extraordinary diversity present in planetary systems across the cosmos. HD 189733b, a vivid blue exoplanet located 63 light-years away in the constellation Vulpecula, provides a striking contrast to Earth despite its similar azure hue. Unlike Earth, where the blue color of the sky comes from Rayleigh's scattering of sunlight by the atmosphere, the blue tint of HD 189733b is due to its exotic weather conditions and atmospheric composition. This scorching hot Jupiter, which orbits very close to its host star, experiences surface temperatures of around 1,800 F, leading to some truly otherworldly phenomena. One of the most fascinating aspects of HD 189733b's atmosphere is the presence of silicate particles and condensed metals such as magnesium silicate in its upper atmosphere. These tiny particles can form clouds and rain droplets of molten glass. When these glass particles fall through the atmosphere, they scatter blue light more effectively than other wavelengths due to their size and the specific optical properties of silicates, which result in the planet's distinctive blue coloration. Moreover, the extreme atmospheric conditions on HD 189733b lead to high-speed winds estimated to blow at over 4,300 miles per hour. These intense winds would make the falling molten glass rain a horizontal torrent, adding to the planet's hazardous environment. The combination of high temperatures, silicate-rich clouds, and violent winds creates a unique system where blue-colored rain of molten glass hurtles through the atmosphere. This not only contributes to the planet's blue appearance, but also highlights the diversity of planetary weather systems and the complex interactions between atmospheric chemistry and local conditions in exoplanetary environments. As instruments and observational techniques advance, further studies of such exotic worlds will continue to expand our understanding of the varied and often extreme climates that exist beyond our solar system. The concept of diamond rain on Neptune and Uranus is one of the most fascinating phenomena in planetary science. This otherworldly weather is driven by the unique conditions found deep within these ice giants. Both planets possess a thick atmosphere composed primarily of hydrogen and helium, with substantial amounts of methane, ammonia, and water. It is the presence of methane in particular that sets the stage for this extraordinary meteorological event. Methane molecules consist of one carbon atom bonded to four hydrogen atoms. Under the extreme pressures and temperatures found thousands of kilometers below the surface of Neptune and Uranus, around 7,000 F, the methane is believed to break apart. Here, the intense environmental conditions cause the carbon atoms to be released from the methane molecules. As the pressures increase, these free carbon atoms are squeezed together into crystalline structures forming diamonds. These diamonds then rain down through the planet's interiors, falling potentially thousands of kilometers. This diamond rain isn't just a poetic idea, it's supported by experimental evidence from labs on Earth. Scientists using high-pressure devices like shock compression techniques have successfully recreated the extreme conditions of the deep interiors of Neptune and Uranus. These experiments show that under such intense pressure, carbon indeed forms diamond-like structures. Moreover, the presence of diamond rain suggests a dynamic and active interior for these ice giants. As diamonds descend toward the planet's cores, they generate frictional heat, which may contribute to the thermal profile and possibly the magnetic fields of Neptune and Uranus. This phenomenon underscores the exotic and diverse nature of planetary processes, illustrating how different worlds can exhibit behaviors that are almost unimaginable within the context of our own earthly experience. Understanding these mechanisms not only enriches our knowledge of Neptune and Uranus, but also offers insights into the possible interior dynamics of exoplanets with similar compositions, expanding our grasp of planetary science across the galaxy. Kelt 9b is an extraordinary exoplanet that shatters many conventional notions about planetary climates. Discovered in 2016, this gas giant orbits its star Kelt 9, a luminous A-type star every 5 days. Due to its extremely close proximity to its host star, Kelt 9b endures one of the harshest environments known, with its dayside temperature soaring to a blistering 7,800 F. This incredible heat makes the day side of Kelt 9b hotter than some stars, including red dwarf stars, which typically have surface temperatures around 6,000 F. Several factors contribute to Kelt 9b's extreme thermal environment. Firstly, the planet orbits at a mere 4 million kilometers from its host star, significantly closer than even Mercury is to the Sun. This tight orbit exposes Kelt 9b to an immense amount of radiant energy from its star, which is itself much hotter and more massive than our Sun. The star Kelt 9 emits a substantial amount of ultraviolet radiation, further contributing to the high-energy bombardment of the planet's atmosphere. Additionally, Kelt 9b is tidally locked, meaning one side of the planet constantly faces the star, while the other side remains in perpetual darkness. This results in a significant temperature gradient between the day side and the night side. The intense stellar radiation on the day side prevents any cool down during the night, leading to extreme heating and energetic processes in its atmosphere. The planet's atmosphere is composed of hydrogen and other elements that get ionized and dissociated under such high temperatures, creating a plasma-like environment. Observations also suggest that these extreme conditions lead to complex atmospheric dynamics, including strong winds that redistribute some of the heat around the planet. The study of Kelt 9b offers profound insights into the physics of exoplanets under extreme conditions and showcases the diverse and often surprising nature of planetary science. Understanding these high-temperature environments extends our knowledge of planet-star interactions and the potential atmospheric compositions that can result, enriching our broader comprehension of exoplanetary systems throughout the galaxy. Imagine a world where the sky hosts not one but two suns, dancing around each other in an intricate celestial ballet. This is the reality for Kepler 16b, a planet situated 200 light-years away from Earth that orbits not just one but two stars. This type of phenomenon is known as a circumbinary planet, a marvel in the cosmos where a single planet orbits a pair of stars. Kepler 16b, roughly the size of Saturn, showcases how intricate gravitational forces can orchestrate stability amid what seems like chaos. The two suns it orbits are a pair of stars locked in a tight gravitational dance, completing an orbit around each other every 41 days. But how does this planet manage such a feat without being torn apart by the conflicting gravitational pulls of its twin suns? The answer lies in the delicate balancing act of gravitational forces and orbital resonance. The two stars create a combined gravitational field rather than individual ones, permitting Kepler-16b to travel in a stable path around the barycenter of this dynamic duo. This barycenter is the point around which the stars themselves orbit, generating a more unified force that acts on the planet. Despite its distance, circling the stars at a distance equivalent to the orbit of Venus around our Sun, Kepler-16b remains in a stable orbit thanks to this complex interplay of forces. The planet's stable yet extraordinary journey around two suns expands our understanding of the possible configurations in our ever-mysterious universe. Dubbed Methuselah, after the biblical figure reputed for his long life, the planet PSR-B 1620-26b stands as a celestial testament to the longevity possible in the cosmos. This ancient world orbits a unique duo of dead stars, a pulsar and a white dwarf. Methuselah's age, estimated to be around 7 billion years, makes it one of the oldest planets ever discovered. But what factors contribute to this extraordinary age? For most planets, their life cycle is intimately tied to the life cycle of their parent stars. Methuselah, however, found itself in an exceptional scenario. Formed in the early universe, it originally orbited a main sequence star much like our Sun. But as the universe aged, changes occurred. The star evolved into a red giant and finally into a white dwarf. Later, the planetary system encountered a pulsar, a type of neutron star known for its rapid rotation and intense magnetic field. Due to the gravitational interactions within the densely packed environment of its home, the globular cluster M4, this stellar encounter led Methuselah to adopt a new, albeit unusual, cosmic relationship with the pulsar and white dwarf. The stability within the dense globular cluster and the ancient origin of its stars collectively hint at Methuselah's incredible age. In this cosmic interplay, the planet's continued orbit around these stellar remnants through time essentially grants it the age it holds today, providing a fascinating glimpse into the early universe. WASP 107b, intriguingly known as a superpuff planet, exhibits characteristics that challenge our traditional understanding of planetary formation. Situated about 212 light-years from Earth in the constellation Virgo, WASP 107b is approximately the size of Jupiter, but is uniquely over 10 times less dense. To picture this anomaly, imagine a planet with the girth of our gas giant, yet possessing the mass closer to that of a smaller icy planet like Neptune. The extraordinary formation of WASP 107b hints at an unconventional path in the planet-building processes. The perplexing nature of WASP 107b can partly be explained by its atypically massive, extended atmosphere. During its formative years in the protoplanetary disk surrounding its star, the core of WASP 107b might have accumulated a significant amount of gas before substantial planetary migration occurred. Yet its core mass, much smaller than expected for the amount of gas enveloping it, suggests an unusual efficiency in gas accretion. It is as though it efficiently captured and held this massive atmosphere despite a relatively modest initial core. Additionally, its close orbit, positioned merely 8 million kilometers from its star, may contribute to the bloated nature of its atmosphere through the process of atmospheric inflation driven by the star's intense heat. These factors, combined with efficient gas capture by a smaller-than-expected core and the contribution of stellar heat, have ensured WASP 107b's designation as a superpuff planet. This celestial oddity not only invites deeper inquiry into the diversity of planetary systems, but also challenges existing models of gas giant formation, expanding our comprehension of the myriad ways in which planets can evolve and thrive in the universe. HD 189733b, a gas giant located 64 light-years away in the constellation Vulpecula, is a world of extremes. Its weather patterns are nothing short of astonishing, characterized by howling winds reaching speeds of up to 5,400 miles per hour. To put that into perspective, these winds blaze at speeds nearly 7 times that of the fastest hurricanes on Earth. This tempestuous activity finds its roots in the planet's close proximity to its parent star. and the resulting dramatic temperature differences across its surface. Classified as a hot Jupiter, HD 189733b orbits its star at a blistering pace, completing one orbit in just over 2 Earth days. The planet is tidally locked, beholden to the same fate as our moon with Earth, showing the same face to its sun at all times. This locked orientation results in an intensely heated day side and a significantly cooler night side, creating an environment ripe for extreme atmospheric dynamics. Temperatures on the day side soar beyond 2000 F, while the night side experiences relatively cooler conditions. The stark temperature gradient between the two hemispheres generates fierce winds that rush from the blistering day side to the cooler night side in a desperate attempt to balance the thermal disparity. Additionally, HD 189733b's atmosphere, rich in silicate particles, may further accentuate these dramatic winds. As the intense heat from the star causes these silicates to vaporize, they form clouds that could potentially drive even more vigorous atmospheric circulation. The combination of extreme heat, rapid rotation, and silicate vapor clouds contributes to some of the most ferocious winds known in our cosmic neighborhood, illustrating the tumultuous and dynamic realities of weather on distant exoplanets. Planets like Gordo 7b present a fascinating enigma as they seem to defy the brutal conditions associated with their proximity to their parent stars. Located approximately 489 light-years away in the constellation Monoceros and orbiting its star in just over 20 hours, Gordo 7b is classified as a lava world. This designation arises from the scorching temperatures resulting from its incredibly close orbit, which takes it roughly 23 times nearer to its star than Mercury is to the Sun. Such an extreme orbit initially raises questions about the planet's survivability. The endurance of Gordo 7b in this hellish environment can be attributed to several key factors. First, its composition plays a crucial role. Unlike gas giants that would likely dissipate under such intense heat, Gordo 7b is a rocky planet. Its solid nature, comprising metals and silicates, provides a resilience that gas giants lack. Despite surface temperatures exceeding 4000 F on the star-facing side, which are hot enough to melt rock, Gordo 7b remains intact thanks to its robust makeup. The planet's dense core, rich in heavy elements, offers the necessary gravitational hold to withstand the stellar onslaught. Additionally, the possibility of strong magnetic fields might help in shielding the planet's atmosphere. Although the exact nature and extent of Gordo 7b's magnetic field remain areas of active research, the intense proximity to its star means that any atmosphere it once had might have been blown away by the stellar winds, leaving a naked rocky core. Survival then becomes a matter of stasis rather than thriving. The planet endures through sheer resilience against the continuous barrage of radiation and heat. This ability to persist close to a star offers a stark testament to the range of planetary adaptability, widening our understanding of the diverse conditions under which planets can exist. Gordo 7b's survival in such severe circumstances challenges our preconceived boundaries of planetary habitability and endurance. Gliese 436b, a Neptune-sized exoplanet orbiting the red dwarf star Gliese 436, about 30 light-years away in the constellation Leo, presents a captivating puzzle with its peculiar atmospheric and temperature characteristics. Despite surface temperatures soaring to over 800 F, Gliese 436b intriguingly maintains a significant amount of water ice. This paradox of a hot ice exoplanet has long confounded scientists and sparked curiosity about the physics underlying its atmosphere. The key to understanding this phenomenon lies in the extreme pressures at play within the planet. Gliese 436b's considerable gravitational pull forces water into a phase known as Ice 7, or superionic water. Here, the water molecules are densely packed due to the immense pressure, causing them to remain solid despite the searing temperatures. Effectively, the planet hosts a form of water ice that wouldn't typically exist under Earth's atmospheric conditions, defying our conventional expectations of states of matter. Adding another layer of intrigue are the emissions and potential atmospheric compositions. Observations suggest that Gliese 436b possesses an atmosphere rich in hydrogen, which could contribute to its heat retention while the underlying high-pressure ice remains solid. Additionally, the feasibility of methane and other volatiles in the atmosphere presents a further anomaly, given that such compounds often break down at the temperatures observed. The planet's unique atmospheric properties suggest a complex interplay of gravitational compression, chemical composition, and heat transfer, making Gliese 436b an extraordinary laboratory for examining the limits of planetary physics. This unusual concoction of circumstances redefines our understanding of gas giants and ice giants alike, pushing the boundaries of what planetary atmospheres and surfaces can withstand. At the heart of our Milky Way lies an awe-inspiring and formidable entity known as Sagittarius A, a supermassive black hole. Astronomers have identified this colossal object by observing its profound gravitational effects on nearby stars and gas clouds. Sagittarius A itself remains invisible because no light can escape its intense gravitational pull, but the energetic dance of matter around it offers compelling evidence of its presence. This cosmic behemoth boasts a mass approximately 4 million times that of our Sun, compressed into a region no larger than the orbit of Mercury, an extraordinary testament to the mysterious and powerful nature of black holes. The environment surrounding Sagittarius A is nothing short of extreme. As gas and dust swirl towards the black hole, they form an accretion disk, heating up to millions of degrees due to intense friction and gravitational energy. This superheated material emits X-rays and other high-energy radiation that astronomers detect using space-based observatories. The immense gravitational forces also catapult stars into high-speed orbits, some reaching velocities of up to several thousand kilometers per second. The study of these stars in close orbits around Sagittarius A has been crucial in pinpointing not only the mass, but also the location of this supermassive black hole. In addition, recent detections of flares and sudden bursts of radiation from the region hint at even more dramatic interactions occurring just outside the event horizon, the boundary beyond which nothing can escape. These observations provide a captivating yet incomplete picture, driving scientists to push the boundaries of technology and theory to understand the complexities of galactic centers. As we continue to probe Sagittarius A, we edge closer to unlocking the secrets not just of our own Milky Way, but of black holes and galactic cores throughout the universe. The formation of supermassive black holes, enigmatic giants anchoring the hearts of galaxies, remains one of the most fascinating and complex puzzles in astrophysics. These titans, with masses ranging from millions to billions of times that of our Sun, likely have multifaceted origins, drawing from several proposed mechanisms, each contributing to the grand cosmic tapestry. One prominent theory is that supermassive black holes formed from the collapse of massive primordial gas clouds in the early universe. These gas clouds, bereft of metals and other elements that would radiatively cool and fragment the collapsing material, could circumvent the usual star formation process, collapsing directly into black holes with masses on the order of thousands of solar masses. Such direct collapse black holes could then rapidly amass more material, growing to supermassive sizes in a relatively short cosmological timespan. Another exciting pathway involves the merger and accretion processes occurring in dense stellar environments. In the crowded cores of young galaxies and protogalaxies, frequent collisions and mergers of massive stars could lead to the creation of intermediary mass black holes. These black holes would then sink to the galaxy's center due to dynamical friction, interacting gravitationally with less massive stars and subsequently merging to form a supermassive black hole. Once situated at the galactic core, the black hole would continue to grow by feeding on gas, stars, and even other black holes through a process known as accretion. Moreover, the recent observations of gravitational waves have unveiled the role of hierarchical mergers, a process where black holes merge repeatedly over cosmic time, creating increasingly massive black holes. These multifaceted processes, direct collapse, accretion, and hierarchical mergers, likely worked in concert to produce the supermassive black holes we observe today. By delving into these formation theories, Astronomers can piece together the evolutionary history of these cosmic giants, shedding light not just on the black holes themselves, but also on the galaxies they inhabit, offering a broader understanding of our universe's dynamic and intriguing nature. The Cartwheel Galaxy presents a mesmerizing visual of cosmic artistry, displaying a unique wheel-like appearance that sets it apart from typical galaxy formations. This extraordinary structure is primarily the result of a dramatic galactic collision, a cataclysmic event that unfolded hundreds of millions of years ago. The key to understanding the Cartwheel Galaxy Alcest's unusual shape lies in its violent past and the ensuing gravitational interactions. Located about 500 million light-years away in the constellation Sculptor, the Cartwheel Galaxy once likely resembled a standard spiral galaxy. However, it underwent a transformative encounter when a smaller galaxy barreled through its core. This high-speed collision sent powerful ripples of gravitational shock waves radiating outward, much like the ripples seen when a stone is tossed into a pond. These waves compressed the interstellar gas and dust, triggering a wave of new star formation that spread outwards in a ring-like fashion from the point of impact. The result of this colossal interaction is a distinct ring of hot young stars encircling the Galaxy S center, giving the Cartwheel Galaxy its iconic appearance. This ring is generally referred to as a starburst ring because of the intense star formation it is witnessing. Compounding the central ring are the Galaxy S spiral arms, now distorted and elongated due to the gravitational forces at play. The remnants of the impacted galaxy, and possibly some of its stars, have likely been flung into the outskirts or even merged with the Cartwheel Galaxy. Further observations using multi-wavelength astronomy, spanning X-rays, ultraviolet, optical, and infrared light, reveal the dynamic processes in the Cartwheel Galaxy S core and its outer ring. These insights illustrate the dramatic and complex nature of galactic interactions, where colliding galaxies can dramatically reshape and redefine their structure, resulting in celestial masterpieces like the Cartwheel Galaxy. Galaxies like NGC 1277, often referred to as red and dead galaxies, are fascinating relics from an earlier era of the universe. Located around 220 million light-years away in the Perseus cluster, NGC 1277 is notable for its population of old stars with little evidence of recent star formation. This ancient stellar composition offers a glimpse into the history of galaxy formation and evolution. The formation of such galaxies is thought to occur in stages, influenced by both intrinsic properties and external factors. In the early universe, NGC 1277 likely underwent a rapid and intense period of star formation, catalyzed by the abundant gas reservoirs available during that epoch. This period, known as a starburst phase, would have consumed substantial amounts of gas in a relatively short time, producing a dense, compact galaxy filled with massive young stars. These early bursts of star formation resulted in the production of many of the heavy elements present in the galaxy today. However, what set NGC 1277 apart is the relatively quick cessation of star formation. Several mechanisms could explain this quenching process. One possibility is that the galaxy exhausted its gas supply during the starburst phase, leaving little material for new stars to form. Another factor could be environmental influences, such as interactions within the dense Perseus cluster. NGC 1277 might have experienced gravitational encounters with other galaxies or the hot intracluster medium, stripping away its remaining gas through a process known as ram pressure stripping. Additionally, supermassive black holes residing at the centers of galaxies like NGC 1277 can play a crucial role. These colossal entities can heat the surrounding gas through energetic outflows and radiation, preventing it from cooling and collapsing to form new stars. This process, known as feedback, can effectively quench further star formation. As a result, NGC 1277 transitioned into a phase dominated by its old stellar population. These stars, formed billions of years ago, now constitute the majority of the Galaxy S mass, giving NGC 1277 its characteristic appearance, dominated by older red-hued stars. Studying such galaxies helps astronomers understand the evolutionary pathways that galaxies can take. shedding light on the various processes that can lead to the cessation of star formation and the maturation of galaxies over cosmic time. The immense voids in the universe are vast, sparsely populated regions of space that stand in stark contrast to the densely packed galaxy clusters and filaments that weave the cosmic web. These voids, which can span hundreds of millions of light-years, are some of the most mysterious and intriguing structures in the cosmos. One of the largest known voids, the Botez void, is a colossal region nearly 330 million light-years in diameter, containing only a handful of galaxies. Understanding how these vast empty spaces form and persist is a key challenge for cosmologists. Voids are believed to originate from tiny fluctuations in the density of matter in the early universe. These fluctuations, amplified by the expansion of the universe, created regions with slightly higher and lower densities. Over billions of years, gravity caused the denser regions to collapse and form galaxies, clusters, and filaments, while the less dense regions expanded, becoming the voids we observe today. The properties of these voids can provide crucial insights into the fundamental physics of the universe. For instance, the distribution and structure of voids are influenced by dark energy, the mysterious force driving the accelerated expansion of the universe. By studying voids, astronomers can learn more about the nature of dark energy and its effects on the large-scale structure of the cosmos. Additionally, voids can serve as cosmic laboratories for testing theories of gravity and the behavior of dark matter. Because these regions are relatively empty, they are less affected by the complex gravitational interactions that dominate galaxy clusters, making them ideal for studying the underlying properties of the universe. Furthermore, voids can offer unique opportunities to study the intergalactic medium, the diffuse gas that exists between galaxies. The low-density environments of voids can provide a clearer view of this gas, which is otherwise difficult to observe in denser regions. By examining the intergalactic medium in voids, scientists can gain insights into the processes that govern the formation and evolution of galaxies. In summary, the immense voids in the universe are not just empty spaces, they are crucial components of the cosmic structure that hold valuable clues about the nature of the universe, dark energy, and the fundamental forces that shape the cosmos. The cosmic web and the vast expanses of nearly empty space are among the most compelling features of the universe's large-scale structure. These voids, spanning tens to hundreds of millions of light-years, stand in stark contrast to the dense clustering of galaxies along filaments and nodes. The formation of these colossal voids is fundamentally tied to the intricate interplay of gravity and the initial conditions set by the Big Bang. In the moments following the Big Bang, the universe was a hot, dense sea of nearly uniform matter and radiation. Tiny density fluctuations caused by quantum perturbations during inflation, a rapid expansion of the universe, seeded regions of slightly higher and lower densities. As the universe expanded and cooled, these initial fluctuations snowballed under the influence of gravity. Over time, areas of higher density began to collapse and form galaxies and galaxy clusters, anchoring the cosmic web's filaments and nodes. Meanwhile, regions of slightly lower density evolved in the opposite direction. Lacking sufficient mass to halt their expansion or initiate significant gravitational collapse, these regions progressively emptied out as matter flowed away toward the denser areas. Consequently, the lower density patches expanded into the vast voids we observe today, creating immense empty spaces amidst the interconnected filaments of galaxies. Dark energy, a mysterious force driving the accelerated expansion of the universe, further plays a role in the evolution of cosmic voids. As dark energy propels the overall expansion of space, it accelerates the evacuation of matter from these underdense regions, making the voids even emptier over time. Additionally, simulations of cosmic structure formation, utilizing the principles of dark matter and dark energy, have effectively reproduced the observed distribution of voids. These simulations underscore the critical role dark matter, comprising about 85% of the universe's mass, plays in structure formation. Dark matter, interacting gravitationally but not electromagnetically, guides ordinary matter to clump along the cosmic web. sculpting the vast voids amid the grand structures. By studying these immense voids, astronomers gain valuable insights into the universe's composition, its expansion history, and the fundamental forces shaping its evolution. The cosmic voids serve as a counterpoint to the densely populated regions, offering a complementary perspective on the universe as large-scale structure and the dynamics at play across vast cosmic timescales. Galactic filaments, the immense tendrils of galaxies and dark matter that define the cosmic web, present a remarkable example of the universe's large-scale structure. These colossal formations span hundreds of millions of light-years and form a complex network of nodes and intersections where galaxy clusters reside. The maintenance of these structures over cosmic timescales hinges on several fundamental factors, including gravity, dark matter, and the ongoing interaction with surrounding cosmic environments. At the heart of the filaments, stability lies the gravitational pull exerted by dark matter. Accounting for about 85% of the universe's total mass, dark matter does not emit or interact with electromagnetic radiation, making it invisible and detectable only via its gravitational effects. This unseen component forms the scaffold on which ordinary matter, baryonic matter, clumps together to form galaxies and galaxy clusters. As dark matter congregates along the filaments, it creates gravitational wells that draw in and hold regular matter, reinforcing the filamentary structures. Einstein's theory of general relativity further explains how massive objects warp spacetime, contributing to the gravitational dynamics that maintain the form of these vast filaments. The interplay of gravitational forces ensures that matter flowing through the cosmic web tends to aggregate along these potential wells, continually feeding and reinforcing the filaments. Moreover, the universe's expansion, driven by dark energy, subtly influences these cosmic megastructures. While dark energy propels the accelerated expansion of space, its effect varies with scale. On larger scales, such as between superclusters, dark energy leads to accelerated expansion, pushing structures apart. However, within individual filaments, the gravitational forces from dark matter and baryonic matter dominate, binding the structures together and counteracting the expansive push of dark energy, thus preserving the integrity of the filaments over billions of years. Additionally, ongoing galaxy formation and interactions play a pivotal role. Galaxies within these filaments can experience mergers and accretion, which redistribute matter along the filaments and clusters. These interactions contribute to the dynamical processes that maintain the coherence of the filamentary structure even as individual galaxies evolve. Advanced cosmological simulations, powered by highly sophisticated computational models, have extensively validated these processes. These simulations incorporate dark matter, baryonic matter, gravity, and dark energy to replicate the observed large-scale structure of the universe. The consistency between these theoretical models and actual astronomical observations underscores the robustness of these mechanisms in maintaining the galactic filaments. Through the symbiotic interplay of gravity, dark matter, and cosmic dynamics influenced by dark energy, galactic filaments endure, giving us a window into the universe as grand design stretching across cosmic time and space. The periodic structure of the universe on ultra-large scales, often referred to as the cosmic web, reveals itself through a stunning arrangement of galaxies, clusters, and superclusters interconnected by vast filaments and interspersed with enormous voids. This grand architecture is not random, but rather a well-organized structure that reflects the underlying physical processes that shaped the universe following the Big Bang. The roots of this periodicity can be traced back to the early universe, particularly during the epoch of inflation, a brief period of exponential expansion that occurred fractions of a second after the Big Bang. Inflation stretched tiny quantum fluctuations to macroscopic scales, seeding regions of varying densities in the primordial plasma. These primordial density fluctuations serve as the blueprint for the large-scale structure we observe today. As the universe continued to expand and cool, these initial density variations translated into areas of slightly different matter concentrations. The force of gravity caused the denser regions to attract more matter, growing into galaxies, galaxy clusters, and superclusters, while less dense regions became the vast cosmic voids. This process of gravitational collapse and clustering over billions of years gave rise to the interconnected cosmic web structure. A pivotal phenomenon contributing to this structure is known as baryon acoustic oscillations (BAOs). In the early universe, the interplay between matter and radiation created sound waves that propagated through the hot, dense plasma. These oscillations left imprints in the distribution of matter when electrons and protons combined to form neutral hydrogen, allowing radiation to decouple and escape as the cosmic microwave background. The characteristic scale of these acoustic waves now manifests as a slight preferential separation between galaxies, providing a standard ruler for cosmological measurements. Dark matter, making up about 27% of the universe's total mass energy content, further plays an indispensable role in shaping the periodic structure. Dark matter does not interact with light, but exerts gravitational influence, forming a scaffolding that guides the clumping of normal matter, baryonic matter, through processes governed by gravity. Regions rich in dark matter became sites for galaxy formation, reinforcing the periodic patterns set by the primordial fluctuations and BOs. Dark energy, constituting about 68% of the universe, influences the large-scale structure by driving the accelerated expansion of the universe. While dark energy tends to push structures apart on the largest scales, its impact is more pronounced in the vast voids between the filaments and clusters, subtly altering the periodic arrangement over cosmic time. By combining observations from telescopic surveys and simulations, scientists find a congruence between theoretical models and actual data, confirming the periodic structure of the cosmic web. These models integrate the effects of inflation, BAOs, dark matter, and dark energy, offering a coherent picture of how the universe's large-scale periodic structure originated and evolved, presenting a remarkable testament to the underlying unity and complexity of cosmic evolution. Galaxy clusters like El Gordo, whose name translates to the fat one in Spanish, are among the largest and most massive structures in the universe. Located approximately 7 billion light-years away, El Gordo is an extraordinary example of a galaxy cluster, boasting a mass roughly 3 quadrillion times that of the Sun. The formation of such colossal clusters is a testimony to the intricate processes of cosmic evolution, governed primarily by the interplay of gravity, dark matter, and dark energy. The formation of El Gordo and galaxy clusters in general begins with the gravitational collapse of dark matter in the early universe. Dark matter, which makes up about 85% of the universe's matter, doesn't interact with electromagnetic radiation, so it remains invisible, detectable only through its gravitational effects. In the aftermath of the Big Bang, dark matter began to clump together under the influence of gravity, forming halos that acted as gravitational wells. These dark matter halos attracted baryonic matter, ordinary matter composed of atoms, leading to the formation of galaxies within them. Over time, smaller halos merged to form larger aggregates, a process known as hierarchical clustering. Through repeated mergers and accretions, these massive structures coalesced into the galaxy clusters we observe today. El Gordo is thought to have formed through the collision and merging of 2 smaller galaxy clusters, an energetic process that creates shock waves observable in various wavelengths, including X-rays. Strong evidence for El Gordo's formation through such a collision comes from observations of its hot intra-cluster gas. El Gordo's gas emits X-rays detected by telescopes like NASA's Chandra X-ray Observatory. These observations reveal a turbulent distribution of hot gas, indicative of a high-energy collision. The gas in El Gordo is extremely hot, reaching temperatures of tens of millions of degrees, and it exhibits shock waves and compression features that are telltale signs of massive cluster mergers. Moreover, the distribution of dark matter within El Gordo has been mapped using gravitational lensing, a phenomenon predicted by Einstein's general relativity, where massive objects warp the fabric of space-time, bending and magnifying the light from more distant objects. These gravitational lensing observations show an extended, clumpy distribution of dark matter, further supporting the scenario of a recent and violent collision between galaxy clusters. Dark energy, the mysterious force driving the universe's accelerated expansion, also plays a role, though more subtly. While dark energy tends to push galaxy clusters apart on the largest scales, within the clusters themselves, gravitational forces dominate. The accelerated expansion due to dark energy affects the rate at which galaxy clusters can grow, limiting how quickly they can attract additional material from substructures. Gordo's immense mass and dynamic nature provide a crucial observational anchor for testing cosmological theories and models. By studying such galaxy clusters, astronomers gain insights into the nature of dark matter, the effects of dark energy, and the processes of galaxy formation and evolution over cosmic time. Observations of Gordo and similar clusters help refine our understanding of the universe as large-scale structure and the forces shaping its evolution. High-velocity clouds HVCs in galactic halos present an intriguing and complex puzzle in the field of astrophysics. These massive concentrations of gas exhibit velocities that significantly differ from the regular rotational movement of their host galaxies. The exact origins of HVCs are multifaceted, involving several potential sources and processes that contribute to their presence in the galactic halo. One prominent theory suggests that HVCs originate from the galactic fountain mechanism. In this process, ongoing star formation and supernova explosions within a Galaxy S disk generate powerful stellar winds and shock waves that eject gas into the galactic halo. As this gas cools and loses energy, it eventually falls back toward the Galaxy S disk, sometimes at high velocities. This cycling of gas between the disk and halo plays a critical role in regulating star formation and redistributing chemical elements within the galaxy. Another possible source of HVCs is gas accretion from the intergalactic medium IgM. Galaxies are not isolated systems, they continually interact with their surrounding environments. Cold gas from the IgM can be pulled into a Galaxy-S gravitational influence, streaming toward the halo at high velocities. This infalling gas can replenish the Galaxy S star-forming material and contribute to the overall growth and evolution of the galaxy. HVCs may also result from the tidal interactions and mergers between galaxies. When galaxies encounter each other, their gravitational fields can distort and strip away gas from their disks, flinging it into the halo at high velocities. These interactions are particularly common in galaxy clusters, where galaxies move through a dense intergalactic environment and frequently interact with each other. Furthermore, HVCs could be remnants of earlier galaxy formation processes. During the early stages of a Galaxy S evolution, gas clouds that did not form stars could remain in the galactic halo, maintaining high velocities due to the initial conditions of their ejection or collapse. Observational evidence for these theories comes from a variety of sources, including radio observations of neutral hydrogen using facilities like the Arecibo Observatory and the Green Bank Telescope. These observations reveal the spatial distribution, velocity, and physical properties of HVCs, offering insights into their origins and relationships to the host galaxies. The study of HVCs also benefits from simulations and theoretical models that replicate the interactions and evolution of gas in galactic halos. Overall, the presence of HVCs highlights the dynamic and ongoing processes that shape galaxies. Their study provides important clues about the mechanisms of gas recycling, accretion, and interaction in the universe, deepening our understanding of galaxy formation and evolution over cosmic time. Through continued observations and research, astronomers aim to unravel the complex origins and roles of these enigmatic high-velocity clouds in galactic halos. The NE occurs around an energy of approximately 1 quadrillion electron volts. This feature is believed to be related to the limits of acceleration mechanisms within our galaxy. One leading hypothesis posits that the NE marks the energy beyond which supernova remnants, long considered primary accelerators of cosmic rays, can no longer effectively accelerate particles. As cosmic rays reach higher energies, they struggle to be confined by the magnetic fields within the remnants, leading to a steeper drop in their abundance beyond the NE. Additionally, at these energies, particles begin to escape the Galaxy S magnetic field more easily, reducing their likelihood of being detected on Earth. The ankle, appearing at even higher energies around 10 quintillion electron volts, presents a different puzzle. This feature is often interpreted as the transition point where the dominant sources of cosmic rays switch from galactic to extragalactic origins. Above this energy, cosmic rays are thought to emanate from powerful extragalactic sources, such as active galactic nuclei or gamma-ray bursts. These ultra-high energy particles traverse vast intergalactic distances, and their observed flux is influenced less by galactic confinement and more by the universe's large-scale structure and magnetic fields. The ankle signifies where the flux flattening occurs, hinting at the arrival of cosmic rays from sources far beyond our Milky Way, thus bridging our understanding of both galactic and extragalactic cosmic phenomena. Solar cosmic rays and galactic cosmic rays, while both high-energy particles, originate from distinctly different sources and possess unique characteristics that set them apart. Solar cosmic rays, also known as solar energetic particles (SEPs), are primarily generated by the Sun. These particles are typically accelerated during solar flares and coronal mass ejections (CMEs), events that release immense amounts of energy and propel charged particles, mainly protons and helium nuclei, out into the solar system. Solar cosmic rays tend to have relatively lower energies compared to their galactic counterparts, usually in the range of tens to hundreds of millions of electron volts. The intensity of SEPs is often related to the solar cycle, peaking during periods of high solar activity, which occurs approximately every 11 years. On the other hand, galactic cosmic rays (GCRs) originate from far outside our solar system, likely from supernova remnants, pulsars, and other high-energy astrophysical sources scattered throughout our galaxy. These particles travel vast distances through the interstellar medium before reaching Earth and are composed of a broader array of elements, ranging from hydrogen to heavier elements like iron. Unlike solar cosmic rays, GCRs possess incredibly high energies, often reaching billions and even trillions of electron volts. Their interaction with the Earth's atmosphere and magnetic field contributes significantly to the background radiation experienced at ground level and high altitudes. Furthermore, because of their differing origins, solar and galactic cosmic rays interact with the heliosphere, the bubble-like region of space dominated by the solar wind, in unique ways. The solar wind modulates the flux of GCRs, with solar activity influencing how many galactic cosmic rays can penetrate deep into the inner solar system. During periods of high solar activity, the enhanced solar wind and magnetic field provide a greater shielding effect, reducing the intensity of GCRs that reach Earth. Conversely, low solar activity correlates with increased GCR flux. Understanding these variations is crucial for activities such as space exploration, where both types of cosmic rays pose radiation hazards to astronauts and spacecraft. Supernova remnants (SNRs) play a pivotal role in the acceleration of cosmic rays, serving as some of the most powerful natural particle accelerators in the galaxy. When a massive star reaches the end of its life, it undergoes a catastrophic explosion known as a supernova, releasing a tremendous amount of energy and stellar material into space. The resulting expanding shock waves plow through the surrounding interstellar medium, creating the structure known as a supernova remnant. Within the shock front of a supernova remnant, the process of diffusive shock acceleration takes place. As particles, primarily protons and atomic nuclei, encounter the shock wave, their energies increase significantly through repeated interactions with the magnetic fields. These particles gain energy by crossing and recrossing the shock front, colliding with turbulent magnetic fields on both sides of the shock. With each crossing, their velocity increases, effectively turning the shock front into a formidable particle accelerator. This process continues until the particles reach relativistic speeds, nearing the speed of light, and are eventually able to escape the magnetic confinement of the remnant and propagate across the galaxy as cosmic rays. Observations of certain supernova remnants, such as Cassiopeia A and Tycho, have provided substantial evidence supporting this acceleration mechanism. High-energy gamma rays detected from these remnants are believed to be produced by the interactions of accelerated particles with the surrounding matter and magnetic fields. These gamma rays serve as indirect evidence of the presence of high-energy cosmic rays. Supernova remnants, therefore, not only contribute significantly to the pool of galactic cosmic rays, but also play a crucial role in our understanding of the processes that govern high-energy astrophysics and the life cycle of stars. Cosmic rays, which are high-energy particles originating from sources such as the Sun, supernova remnants, and distant galaxies, have a significant impact on space weather, a collection of conditions and phenomena in space that can affect Earth and its technological systems. Primarily, cosmic rays interact with the space environment around Earth, contributing to the complex dynamics of the heliosphere, magnetosphere, and ionosphere. In the heliosphere, the bubble-like region of space influenced by the solar wind, cosmic rays are modulated by the solar activity cycle. During periods of high solar activity, the enhanced solar wind and stronger solar magnetic fields act as a shield, reducing the influx of galactic cosmic rays. Conversely, during solar minimums, when solar activity is lower, the heliospheric shielding effect diminishes, leading to an increased flux of cosmic rays reaching Earth's vicinity. These variations in cosmic ray intensity influence the overall radiation environment in space, which is a critical consideration for spacecraft electronics and the health of astronauts. Cosmic rays also play a role in generating space weather disturbances by interacting with Earth's magnetosphere and ionosphere. When high-energy cosmic rays enter the atmosphere, they produce secondary particles such as neutrons and muons that can penetrate deep into the atmosphere and even to the surface. These secondary particles can induce transient ionization bursts in the ionosphere, affecting radio signal propagation and GPS accuracy. Additionally, cosmic rays can affect the formation and dynamics of clouds, potentially influencing weather patterns and climate over longer timescales. The continuous bombardment of cosmic rays thus underscores the need for advanced space weather forecasting and mitigation strategies, ensuring the protection of both technological infrastructure and human activities in space. Cosmic rays serve as natural probes into the composition and processes of distant galaxies, providing valuable insights that would otherwise be difficult to obtain through traditional electromagnetic observations. When cosmic rays, which are high-energy particles such as protons, electrons, and atomic nuclei, travel through space, they carry with them signatures of the environments they originated from. By analyzing these particles once they reach Earth, scientists can infer important details about the distant astrophysical sources from which they emanated. The composition of cosmic rays, particularly the proportion of different atomic nuclei, can reveal the elemental abundances in distant galaxies. For instance, the presence of elements heavier than hydrogen and helium, such as carbon, oxygen, silicon, and iron, in cosmic rays, indicates the processes of stellar nucleosynthesis and supernova explosions in their source regions. These heavy elements are forged in the cores of stars and released into the galaxy through supernova explosions, spreading the building blocks for planets and life. Therefore, the elemental composition of cosmic rays can offer clues about the star formation rates, types of stars, and the overall chemical evolution of the galaxies they originated from. Furthermore, the energy spectra and isotopic composition of cosmic rays provide additional layers of information. Variations in the energy and isotopic ratios of cosmic rays can inform us about the acceleration mechanisms at play in distant astrophysical sources, such as supernova remnants or active galactic nuclei. The propagation of these high-energy particles through the interstellar and intergalactic medium also leaves distinct imprints, such as spallation reactions, where cosmic rays collide with interstellar atoms, breaking into lighter elements and isotopes that can be detected upon their arrival at Earth. Ultimately, cosmic rays offer a unique window into the distant cosmos, revealing the intricate processes governing the life cycle of matter on both galactic and intergalactic scales. Cosmic rays, those high-energy particles from outer space, interact intriguingly with Earth's magnetic field, shaping their trajectories and influencing their impact on our planet. As these particles, which include protons, electrons, and atomic nuclei, approach Earth, they encounter the geomagnetic field, a dynamic and protective shield generated by the movement of molten iron within our planet's core. When cosmic rays enter the vicinity of Earth, their paths are altered by the magnetic field due to the Lorentz force, which acts perpendicular to both their velocity and the magnetic field lines. This interaction causes charged particles to spiral and bend along the magnetic field lines, making it harder for them to penetrate directly to the surface. The effectiveness of this shielding is not uniform. It varies with latitude and the strength of the local magnetic field. Near the equator, where the magnetic field is strongest and horizontal to Earth's surface, cosmic rays are more likely to be deflected. In contrast, near the poles, where the magnetic field lines converge and are more vertical, cosmic rays can more easily penetrate the atmosphere. The spokes in Saturn's rings are among the most mysterious and captivating features observed within the gas giant's magnificently complex ring system. These transient radial features appear as ghostly striations that rotate along with the ring particles, temporarily marring the otherwise smooth structure of Saturn's rings. Discovered by the Voyager spacecraft in the early 1980s and later studied in greater detail by the Cassini mission, these spokes are believed to be primarily electrostatic phenomena. The leading hypothesis for the creation of these spokes revolves around the interaction between the ring particles and Saturn's powerful magnetic field. The smallest particles in Saturn's rings, primarily dust-sized grains, can become electrically charged due to interaction with solar ultraviolet radiation or energetic particles trapped in the planet's magnetosphere. As these tiny particles acquire an electric charge, they can be influenced by Saturn's magnetic field, causing them to lift slightly above the ring plane and align along magnetic field lines. This process involves several complex steps. First, when charged ring particles interact with the magnetic field, they experience a Lorentz force, which can lift them from the ring's surface. The lifted particles form the visible spoke structures by scattering sunlight differently than the surrounding uncharged particles, making spokes conspicuous against the background of the rings. The variations in light scattering cause the spokes to appear darker or lighter than the adjacent regions of the rings, depending on the angle of observation and illumination. Seasonal changes on Saturn also influence the formation and visibility of the spokes. They are more prominently observed around the equinoxes when Saturn's equatorial plane, and thus its rings, is aligned edge-on with the Sun. During these times, the Sun's ultraviolet radiation efficiently charges the ring particles, enhancing the conditions needed for spoke formation. As Saturn shifts through its seasons, the incidence and visibility of the spokes vary, explaining why they are not always observable. Another intriguing aspect of the spokes is their dynamic behavior. They can form and dissipate over a matter of hours or days, moving across the rings in synchronization with Saturn's rotation. This rapid formation and disappearance further indicate the delicate balance controlled by the interaction between electromagnetic forces and the material composition of the rings. Understanding the behavior and mechanics behind these spokes offers critical insights into the interactions between the solid and plasma environments within the ring system. These observations have broader implications for planetary ring systems and the study of dust dynamics in various astrophysical contexts, contributing to our knowledge of how electromagnetic forces can shape and influence celestial environments. Pluto's heart-shaped feature, known as Tombaugh Regio, stands as one of the most striking and iconic surface features on this distant dwarf planet. Named after Clyde Tombaugh, the astronomer who discovered Pluto in 1930, this vast region comprises two major lobes with distinct geological characteristics. The left lobe, called Sputnik Planitia, is an enormous basin filled with nitrogen, methane, and carbon monoxide ices, while the right lobe extends into rugged mountainous terrain. The formation of Sputnik Planitia, the western lobe of Tombaugh Regio, is believed to be related to both endogenic and exogenic processes, meaning internal and external influences. A leading hypothesis suggests that Sputnik Planitia is the result of a massive impact event billions of years ago. An asteroid or comet could have struck Pluto, creating a huge basin. Over time, this basin became a cold trap for volatile ices due to its low elevation and the unique climatic conditions on Pluto. This accumulation of ices likely led to isostatic adjustment, where the crust rebounded and the basin's floor was infilled, creating the smooth, icy plains observed today. Interestingly, Sputnik Planitia is not just a passive deposit of ices, it is geologically active. The plane exhibits a pattern of polygonal cells, likely caused by convection within the nitrogen ice. These convective patterns suggest that the ice is slowly being renewed and resurfaced by the movement of material driven by the slow but steady heat emanating from Pluto's interior. This process hints at a surprising level of thermal activity for such a distant, cold world. The right lobe of Tombaugh Regio features a more rugged topography, consisting of a mix of nitrogen ice and water ice mountains. The formation of this terrain is less understood, but may involve tectonic processes, sublimation, and the unique interplay between different types of ice. The region's geological diversity provides crucial clues about the interplay of internal and external forces shaping Pluto's surface. The prominent location of Tombaugh Regio near the equator and its role in influencing Pluto's climate also have significant implications. The bright ices of Sputnik Planitia reflect much of the sunlight, which helps to control the temperature and pressure of Pluto's thin atmosphere. This reflective surface can alter the sublimation and condensation cycles of nitrogen and other volatiles, impacting atmospheric dynamics and contributing to seasonal changes seen on Pluto. The New Horizons spacecraft, which flew by Pluto in 2015, provided the high-resolution images and data that unveiled the complexities of Tombaugh Regio. These observations highlighted unexpected geological activity and diverse surface compositions, challenging previous notions of what small, distant dwarf planets could be like. As scientists continue to analyze New Horizons data and develop models, our understanding of how Tombaugh Regio and similar features form will undoubtedly deepen, offering insights into planetary processes both within our solar system and beyond. The unusual radar reflections from Venus' highlands have intrigued scientists since they were first observed by the Magellan spacecraft in the early 1990s. These highlands, particularly regions like Maxwell Montes, exhibit highly reflective surfaces in radar images, far brighter than the surrounding lowlands. The cause of these radar reflections is a fascinating interplay of Venusian geology and atmospheric chemistry. One leading hypothesis attributes these unusual radar reflections to the presence of metallic or semi-metallic compounds on the highland surfaces. Venus's extremely high surface temperatures, which can reach around 465 C, about 870 F, combined with its dense atmosphere rich in sulfuric acid and carbon dioxide, create a harsh environment where distinctive chemical reactions can occur. In these conditions, minerals may react with atmospheric gases and precipitate out on the cooler highland surfaces. Specifically, the reflective properties observed in radar data are consistent with materials like pyrite, also known as Fool's gold, bismuth, or tellurium-bearing compounds. These materials can form through volcanic outgassing, releasing elements that later condense and settle on the highlands. For instance, the presence of sulfides like pyrite could result from sulfur gases emitted from volcanic activity combining with metallic elements. Another contributing factor could be the presence of a substance that undergoes a phase change at the highland elevations. The cooler temperatures at higher altitudes on Venus, though still hot by Earth standards, could allow certain minerals or metallic compounds to form a solid-state frost, akin to how ice frost forms on Earth's surfaces. This solidified layer can enhance radar reflectivity, making the highlands appear much brighter than the surrounding terrains. Additionally, differences in surface roughness might play a role. Highlands could possess a rougher surface texture at smaller scales, scattering radar waves more efficiently and appearing brighter in radar images. Such enhanced scattering could result from a combination of geological processes like tectonic activity and erosion patterns unique to Venus's high-temperature, high-pressure environment. Data from Magellan's radar mapping, supplemented by observations from other missions like the Arecibo Observatory and Japan's Akatsuki probe, continue to help scientists refine their understanding of Venusian surface properties. Future missions, such as NASA's Veritas and ESA's Envision, aim to provide more detailed radar and spectroscopic studies, which may clarify the exact compositions responsible for the radar reflectivity and offer deeper insights into the geological and chemical processes shaping Venus's enigmatic highlands. Miranda, one of Uranus's innermost and most intriguing moons, showcases a remarkably patchwork-like surface unlike any other celestial body in the solar system. This small moon, just about 480 kilometers, 300 miles in diameter, exhibits a bewildering array of geological features, including giant canyons, terraced layers, and regions known as coronae that appear as large racetrack-shaped bands. This unusual and diverse landscape is a testament to Miranda's complex and violent geological history. One leading hypothesis for Miranda's patchwork appearance is the occurrence of multiple episodes of tectonic activity and cryovolcanism. Early in Miranda's history, tidal forces from its interactions with Uranus and possibly other moons would have generated significant internal friction and heat. This process, known as tidal heating, could have caused the moon's interior to partially melt, leading to convective motion and surface deformation. The coronae, Miranda's most distinctive features, are thought to be the result of upwelling diapirs, which are blobs of warmer ice that rise through the colder, rigid ice shell. These diapirs would push up against the surface, creating the terraced and banded regions observed. The Miranda coronae have concentric ridges and troughs, suggesting that these upwellings cause the surface to stretch and crack, resulting in the distinctive patchwork regions. Additionally, Miranda's large canyons, some of which are up to 20 kilometers 12 miles deep, might have formed from extensional tectonics, a stretching and fracturing of the crust powered by internal processes or tidal interactions. These enormous chasms could have also been exacerbated by past cryovolcanic activity, where volatile substances such as water, ammonia, or methane erupted through the surface, reshaping the terrain dramatically. Another hypothesis considers that Miranda might have undergone a form of catastrophic disruption and reaccretion. This scenario suggests that a significant impact could have shattered the moon, causing it to break apart. The gravitational pull would then reassemble the fragments, creating a body with a highly varied and jumbled surface. This explanation helps account for the high degree of heterogeneity observed across Miranda's surface. Perhaps Miranda's most captivating feature is how it defies traditional geological expectations, showing evidence of resurfacing events across different epochs. The patchwork terrain likely records a tumultuous evolution marked by the interplay of endogenic internal and exogenic external forces. Each geological unit on Miranda's surface appears to tell a story of different eras of tectonic and cryovolcanic activity, making it a fascinating subject for ongoing study. The data we have on Miranda is primarily from the Voyager 2 flyby in 1986, which provided detailed images and invaluable insights into this mysterious moon. Future missions to the Uranian system may offer further understanding of Miranda's geologic history, elucidating the intricate processes that have sculpted its uniquely captivating landscape. The origin of life on Earth is one of the most profound and intriguing questions in science, sparking numerous theories and extensive research. While definitive answers remain elusive, several leading hypotheses offer compelling scenarios for how life might have emerged from non-living chemical processes. One prevailing theory is the primordial soup hypothesis, which suggests that life began in a warm pond or ocean where a mixture of simple organic molecules was subject to energy sources such as ultraviolet light from the sun, lightning, or volcanic activity. This environment could have facilitated the formation of more complex molecules, eventually leading to self-replicating molecules like RNA. Experiments conducted by Stanley Miller and Harold Urey in the 1950s supported this idea by demonstrating that when a mixture of water, methane, ammonia, and hydrogen was exposed to electrical sparks simulating lightning, amino acids, the building blocks of proteins, could form. Another influential theory is the hydrothermal vent hypothesis. This proposes that life may have originated around hydrothermal vents on the ocean floor, where mineral-laden water heated by geothermal processes meets cold ocean water. These environments are rich in energy and chemicals that could promote complex chemical reactions. Indeed, modern hydrothermal vents host diverse ecosystems that thrive without sunlight, relying entirely on chemosynthesis. This habitat creates the conditions where simple organic compounds could react and assemble into more complex molecules, leading to the first living cells. The RNA world hypothesis offers another perspective, positing that RNA, a versatile molecule capable of both storing genetic information and catalyzing chemical reactions, was a crucial step in the origin of life. RNA molecules might have formed spontaneously from simpler precursors, and, due to their catalytic properties, could drive the synthesis of more RNA molecules, setting the stage for natural selection to favor more efficient replicators. Yet another intriguing idea is the concept of panspermia, which suggests that life-S building blocks or even life itself in a microbial form could have originated elsewhere in the cosmos and been delivered to Earth via comets, asteroids, or meteoroids. This theory does not explain how life began, but rather shifts the location of its origin to other celestial bodies. Recent advances in synthetic biology and prebiotic chemistry have provided additional insights. Laboratory experiments have shown that under specific conditions, lipid molecules can self-assemble into vesicles resembling cell membranes, and that amino acids and nucleotides can form peptide bonds and nucleic acids, respectively. These findings suggest that simple protocells, structures that resemble living cells but lack true replication and metabolism, could have arisen from naturally occurring processes on the early Earth. Although each hypothesis has its strengths and challenges, they all contribute to a multifaceted understanding of how life could have originated. As research progresses, combining elements from these different theories may eventually paint a more comprehensive picture of the intricate chemical choreography that led to the dawn of life on our planet, opening new doors in the quest to understand our own origins and the potential for life elsewhere in the universe. While each potential biosignature is intriguing on its own, the most convincing evidence of alien life will likely come from a combination of these indicators reinforcing each other within the context of a planetary environment. The ultimate goal is to build a comprehensive profile that strongly suggests biological processes, enhancing our understanding of life's potential beyond Earth. The quest to determine the prevalence of Earth-like planets in the habitable zone, often described as a region where conditions might be just right for liquid water to exist on a planet's surface, continues to captivate astronomers. This region is crucial because liquid water is considered essential for life as we know it. Advances in space telescopes and observational techniques have significantly expanded our knowledge, bringing us closer to answering this profound question. Data from missions like NASA's Kepler Space Telescope have provided a wealth of information. Kepler, which operated from 2009 to 2018, monitored the brightness of over 150,000 stars, looking for periodic dimming that would indicate an exoplanet transiting in front of its host star. Through its observations, Kepler discovered thousands of exoplanets, including many smaller rocky ones similar in size to Earth. Current estimates based on Kepler data suggest that about 20 to 25 of Sun-like stars harbor at least one potentially habitable Earth-sized planet within their habitable zones. Further insights come from the Transiting Exoplanet Survey satellite TESS, launched in 2018, which continues the search for Earth-like planets around nearby stars. Complementing TESS, ground-based observatories and radial velocity method surveys contribute additional detections and confirmations of such planets, refining our understanding of their frequency. Despite these discoveries, not all planets found in the habitable zone are necessarily Earth-like. Size and location are only part of the criteria. The planet's atmosphere, magnetic field, geological activity, and water presence are crucial factors that determine its habitability. Additionally, the habitable zone's exact range varies depending on the type and activity of the host star. Red dwarfs, the most common type of star in our galaxy, have closer, narrower habitable zones compared to Sun-like stars, but they also exhibit high levels of stellar flares, which can strip away planetary atmospheres. Considering the Milky Way contains an estimated 100 to 400 billion stars, the fraction of stars with potentially habitable planets suggests there could be billions of Earth-like planets in our galaxy alone. This estimation, while promising, is continually refined as more exoplanets are discovered and studied in detail. Astronomers also focus on nearby stars, such as the Proxima Centauri system, to understand the prevalence of Earth-like planets. Proxima Centauri b, a planet orbiting within the habitable zone of the closest star to our Sun, has garnered significant interest. While its exact conditions are still under study, Its discovery supports the idea that such planets might not be rare. Future missions like the James Webb Space Telescope, the European Space Agency's Pluto mission, and increasingly advanced ground-based telescopes like the Extremely Large Telescope and the Giant Magellan Telescope aim to provide more detailed observations. These instruments will help analyze the atmospheres of these Earth-like exoplanets for signs of habitability or even biosignatures, bringing us closer to determining just how common life-bearing worlds might be. Ultimately, while Earth-like planets in the habitable zone appear to be relatively common, confirming their true habitability requires detailed study. As our technology and methods continue to improve, we are likely to refine our understanding of these intriguing worlds and their potential to host life. The idea of life existing in the clouds of Venus is a tantalizing concept that has gained traction among some scientists, despite the planet's notoriously inhospitable surface conditions. Venus, with surface temperatures around 465 C, 869 F, and atmospheric pressure 90 times that of Earth's, seems an unlikely place for life as we know it. However, its upper cloud layers offer a markedly different environment that might be more conducive to the possibility of life. The cloud tops of Venus exist at altitudes where temperatures range from about 30 to 70 C86 to 158 F, and pressures are similar to those found at Earth's surface. This region presents a relatively milder environment compared to Venus's scorched surface. The clouds themselves are primarily composed of sulfuric acid droplets, which are hostile to most known life forms on Earth, but not necessarily beyond the realm of possibility for extremophiles organisms that thrive in extreme environments. Interest in the clouds of Venus as a potential habitat for life surged in 2020 with the reported detection of phosphine gas, a molecule found on Earth as a result of either industrial processes or microbial activity. This discovery, made using the James Clerk Maxwell Telescope and the Atacama Large Millimeter Submillimeter Array, suggested that some form of life could be producing phosphine. On Earth, phosphine is associated with anaerobic organisms, primarily bacteria, living in oxygen-poor environments like swamps and the intestines of animals. The detection of phosphine, however, has been subject to significant scrutiny and debate. Some researchers have questioned the findings, citing potential issues with the observational data and the interpretation of the spectral lines. Regardless, the potential presence of a biosignature gas in Venus's atmosphere has reignited interest in the planet's cloud layers and spurred calls for further investigation. For life to exist in the acidic clouds of Venus, potential organisms would need specialized adaptations. Hypothetical life forms might possess biochemical mechanisms to tolerate, neutralize, or exploit highly acidic conditions. They could also use the particulate matter and the limited water vapor available in the atmosphere to sustain metabolic processes. In some scenarios, these life forms could exist within protective microhabitats or aerosols, tiny droplets that provide a more habitable microenvironment within the broader acidic context. To explore these possibilities, upcoming missions are being designed specifically to study the atmosphere of Venus. NASA's Da Vinci mission and the European Space Agency's Envision mission aim to provide detailed analyses of the planet's atmosphere, surface, and geological activity. These missions will deploy sophisticated instruments capable of detecting and analyzing trace gases, cloud particles, and atmospheric chemistry, offering deeper insights into the potential for life in the clouds of Venus. Understanding whether life can exist on Venus requires exploring a broad array of scientific questions and employing a suite of advanced technologies. While the environment is harsh by Earth standards, the notion that life might find a way to adapt to such extreme conditions continues to drive interest and research, pushing the boundaries of what we consider possible for habitability in the solar system. The potential for life in the subsurface oceans of icy moons within our solar system is one of the most intriguing frontiers in astrobiology. Notable moons such as Europa, orbiting Jupiter, Enceladus, orbiting Saturn, and Titan, also orbiting Saturn, harbor subsurface oceans beneath their icy crusts, offering environments that could be conducive to life. Europa, one of Jupiter's largest moons, is the prime candidate for hosting life. Beneath its ice-covered surface lies a global ocean of liquid water, estimated to be twice the volume of Earth's oceans combined. Evidence for this ocean comes from both the Galileo spacecraft S measurements and the Hubble Space Telescope S observations, which suggest the existence of plumes of water vapor erupting from cracks in the ice. Europa S ocean is thought to be in contact with a rocky seafloor where hydrothermal vents could provide the necessary heat and nutrients for life. On Earth, hydrothermal vents teem with life independent of sunlight, deriving energy from chemical reactions, a process known as chemosynthesis. If similar conditions exist on Europa, it could potentially support microbial or even more complex life forms. Enceladus, a smaller moon of Saturn, also boasts a subsurface ocean beneath its icy shell. The Cassini spacecraft provided detailed evidence of water ice plumes erupting from Enceladus' south polar region, indicating the presence of liquid water beneath the surface. These plumes contain complex organic molecules, salty water, and even tiny silica grains, which suggest hydrothermal activity at the ocean floor. The combination of liquid water, organic molecules, and energy sources makes Enceladus an incredibly promising site for the search for extraterrestrial life. Titan, another moon of Saturn, offers a unique environment with not just one but potentially two types of liquid surface lakes and seas of liquid methane and ethane, and a hypothesized subsurface ocean of water. The surface hydrocarbons present a different chemistry for potential life forms, which might be based on methane solvents rather than water. However, the subsurface ocean, which could be similar in composition to the oceans of Europa and Enceladus, lies beneath a thick ice shell, making it an intriguing target for future exploration. The potential for life in these subsurface oceans depends on several factors: a stable environment with liquid water, the presence of essential chemical compounds like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and a source of energy. In the absence of sunlight, chemical energy from hydrothermal vents or chemical reactions involving the icy materials could support life. The discovery of organic molecules and potential energy sources in the plumes of Enceladus and on the surface of Europa strengthens the case for habitability. Future missions aim to explore these moons in greater detail. NASA's Europa Clipper, set to launch in the 2020s, will perform detailed reconnaissance of Europa's ice shell and subsurface ocean. It will focus on determining the Moon's habitability by studying the ice thickness, ocean composition, and potential hydrothermal activity. Similarly, the proposed Enceladus Life Finder mission aims to directly sample the Moon's plumes for signs of life. Titan will be the focus of NASA's Dragonfly mission, which will send a rotorcraft to explore its diverse surface and atmospheric chemistry. While it will not directly probe the subsurface ocean, it will investigate prebiotic chemistry and methane-based life hypotheses. The exploration of these icy moons offers the potential to uncover environments where life might exist beyond Earth, expanding our understanding of life, its potential adaptability and resilience in extreme conditions. It holds the promise of answering one of humanity's most profound questions: are we alone in the universe? Extremophiles. Organisms that thrive in environments previously thought too extreme for life have significantly broadened our understanding of where and how life can exist, thereby influencing the search for extraterrestrial life. These remarkable organisms not only redefine the limits of habitability on Earth, but also provide crucial insights into potential habitats and survival strategies for life elsewhere in the cosmos. One of the key lessons from Extremophiles is that life can adapt to a wide range of environmental conditions, many of which are analogous to environments found on other planetary bodies. For instance, thermophiles and hyperthermophiles, which reside in extremely hot environments like hydrothermal vents on the ocean floor, suggest that similar habitats might exist on moons like Europa and Enceladus. The presence of hydrothermal activity in the subsurface oceans of these moons, combined with the potential for water-rock interactions, could create niches where microbial life similar to deep-sea extremophiles might thrive. Acidophiles and alkaliphiles, organisms that live in highly acidic or alkaline environments respectively, demonstrate that extreme pH levels are not a barrier to life. This insight is particularly relevant for the exploration of Venus, where the acidic cloud layers could harbor acid-tolerant microorganisms. Similarly, certain features on Mars, such as ancient lake beds with evidence of past acidic conditions, could have supported acidophilic life during wetter periods in the planet's history. Psychrophiles, organisms that live at very low temperatures, and cryophiles, which thrive in cold environments, offer clues about potential life on icy worlds. For example, the ice-covered lakes of Antarctica, where psychrophiles flourish, serve as terrestrial analogues for the frozen surfaces of Europa and Enceladus. These Earth-based environments help scientists understand how life might survive and adapt under perpetual ice, relying on available nutrients and energy sources derived from chemical reactions rather than sunlight. Xerophiles, which can withstand extreme desiccation, provide valuable models for studying potential life on Mars, where the surface is extremely dry. The discovery of brines and recurring slope linii on Mars suggests that temporary wet conditions might exist, analogous to arid environments on Earth, where xerophiles can become metabolically active when water becomes available. Radiation-resistant organisms like Deinococcus radiodurans showcase the incredible resilience of life in the face of high levels of radiation. This trait is particularly pertinent for the potential habitability of Mars and Europa. On Mars, the thin atmosphere offers little protection from cosmic and ultraviolet radiation, making the survival strategies of radiation-resistant extremophiles particularly relevant. Similarly, any life forms beneath Europa's ice shell might be insulated from radiation, suggesting a habitable environment despite the radiation-rich surface conditions. Extremophiles also inform astrobiology about the potential metabolic pathways life might use. Chemoautotrophs, organisms that derive energy from inorganic compounds, suggest that extraterrestrial life might not rely on sunlight but could harness chemical energy through processes like methanogenesis or sulfur reduction. This is particularly relevant for subsurface environments in the solar system where sunlight does not penetrate and chemical energy from hydrothermal vents or rock-water reactions could sustain life. The study of extremophiles continues to drive the development of instruments and missions designed to detect life in extreme environments. For instance, the upcoming Europa Clipper and Mars 2020 missions are equipped with advanced analytical tools, specifically designed with insights from extremophiles in mind. These tools aim to detect biosignatures such as specific molecules, isotopic ratios, or the presence of certain minerals that are commonly associated with life. Extremophiles on Earth have significantly expanded our understanding of the potential for life in the universe. By demonstrating life's resilience and adaptability, they provide valuable models and analogues for potential extraterrestrial habitats, guiding our search for life beyond Earth and informing the design of missions and experiments aimed at uncovering life's potential interplanetary presence. The possibility of silicon-based life forms is a fascinating topic that pushes the boundaries of our understanding of biology and chemistry. While carbon is the foundational element for all known life on Earth due to its versatility and ability to form stable, complex molecules, silicon presents an intriguing alternative. This is largely due to silicon's position directly below carbon on the periodic table, leading to some chemical similarities. However, the arrangement of silicon's electrons and its chemical properties also pose significant challenges. Ongoing research in astrobiology and exoplanet studies helps broaden our understanding of potential life-supporting environments. Missions such as the James Webb Space Telescope aim to analyze the atmospheres of exoplanets for signs of life, looking for unexpected chemical signatures that could indicate non-carbon-based biochemistries. Ultimately, while carbon remains the most probable basis for life as we know and understand it, the exploration of silicon-based life expands the scope of our search for extraterrestrial life. It reinforces the necessity of looking beyond our terrestrial biases and considering a wider array of possibilities in the ever-intriguing quest to understand life in the universe. Detecting technosignatures evidence of technology or technological activities that might indicate the presence of advanced civilizations beyond our planet is a compelling approach in the search for extraterrestrial intelligence. Technosignatures include a broad range of possible indicators, each requiring different methods and instruments for detection. Here are some key technosignatures and how we might go about finding them. 1. Radio signals. One of the earliest and most traditional methods involves searching for narrow-band radio signals. Given that radio waves can travel vast distances across space with relatively little interference, they are a prime candidate for communication attempts. Scientists use radio telescopes to scan the sky for unnatural patterns or signals that could indicate intelligent origin. The Allen Telescope Array and the Green Bank Telescope are examples of facilities that conduct such searches. 2. 3. Optical signals. Another method is to look for powerful laser pulses that might be used for communication or as beacons. Highly coherent light from lasers can stand out against the background of starlight. Instruments like the Laser SETI project aim to detect such signals by scanning large portions of the sky and looking for brief, bright flashes of light at specific wavelengths that could indicate laser activity. 4. 5. Dyson spheres. Advanced civilizations might harness the energy of their stars by building megastructures like Dyson spheres or swarms, which would partially or completely enclose a star. Detecting such structures would involve looking for unusual infrared signatures. A star surrounded by a Dyson swarm would emit less visible light, but more infrared radiation, as the starlight would be absorbed and re-emitted as heat. Infrared surveys like those conducted by the Wide-Field Infrared Survey Explorer WISE spacecraft could potentially identify such anomalies. 6. 7. Artificial satellites and space debris. Observing other star systems for unusual concentrations of artificial satellites, space debris, or even entire space habitats could provide clues. Using high-resolution imaging and spectroscopy to detect unusual objects or reflections moving in non-natural orbits could signal an advanced civilization's activity. 8. 9. Industrial pollutants. Advanced civilizations might produce atmospheric pollutants that can be detected over interstellar distances. For example, certain chemicals, such as chlorofluorocarbons, are industrial pollutants that do not occur naturally in significant quantities. Spectroscopic analysis of exoplanetary atmospheres, searching for signatures of such compounds, could indicate industrial activity. The upcoming James Webb Space Telescope and future telescopes could play a crucial role in this endeavor. 10. 11. City lights. On planets with significant technological development, nighttime city lights might be detectable. These would appear as non-natural, non-periodic brightness variations on the dark side of a planet. Detecting such lights would require very sensitive instruments capable of distinguishing the faint glow of artificial illumination from the planet's natural light. Projects like the Extremely Large Telescope or similar high-resolution instruments could potentially identify these anomalies. 12. 13. Megastructure engineering projects. Large-scale engineering projects like altering the light curve of a star, for example, with a star shade or stellar lifting, could also signal advanced technology. Observing unusual or repetitive patterns in the dimming and brightening of a star's light would suggest large structures or activities altering the starlight. Long-term monitoring of star systems using missions like the Transiting Exoplanet Survey Satellite TESS and future space observatories could help detect these phenomena. 14. 15. Interstellar probes. The detection of interstellar probes, or Bracewell probes, which are autonomous spacecraft designed to seek out and communicate with other civilizations, could indicate intelligent life. Such probes might emit signals or be detectable by their propulsion methods. Current and future space missions might detect these objects if they pass through the solar system, as was done with the object Oumuamua, though no technosignatures were found in that case. 16. The search for technosignatures is inherently multidisciplinary, requiring advances in astronomy, physics, engineering, and data analysis. It also necessitates collaboration across global scientific communities and the strategic use of telescopes and observatories. Enhanced computational techniques, such as machine learning and artificial intelligence, are increasingly relevant, enabling efficient analysis of the vast data sets collected in these searches. As we continue to refine our methods and develop new technologies, the prospect of detecting technosignatures remains an exciting and rapidly evolving field, offering the potential for one of humanity's most significant discoveries, evidence of intelligent life beyond Earth. Our exploration of the cosmos, from the study of cosmic rays to the search for life on distant exoplanets, reveals an ever-expanding understanding of the universe and our place within it. The enigmatic features of Saturn S rings, the heart-shaped region on Pluto, and the mysterious radar reflections on Venus all contribute to a more comprehensive picture of the diverse and dynamic phenomena in our solar system and beyond. The discovery of extremophiles on Earth, capable of surviving in the most inhospitable conditions, provides valuable insights into the potential for life on other worlds. These findings, combined with the tantalizing possibilities suggested by the panspermia hypothesis and the search for technosignatures, push the boundaries of what we consider possible in the quest for extraterrestrial intelligence. As we develop more sophisticated observational tools and embark on ambitious missions, our ability to detect and study these phenomena will continue to grow. Each new discovery brings us one step closer to answering profound questions about the origins of life and the potential for other life forms in the universe. The journey of cosmic exploration is not just a scientific endeavor, but also a testament to human curiosity and the enduring desire to understand the cosmos. The mysteries we unravel and the knowledge we gain will not only enhance our scientific understanding, but also inspire future generations to continue exploring the infinite possibilities of the universe. As we look to the stars, we carry forward the hope and excitement of potentially finding life beyond Earth, enriching our understanding of existence and the grand tapestry of the cosmos.